In this video, we're going to talk about how to remove a node from a binary search tree. Removal is a bit more challenging than insertion. Here's an example. Let's say we want to remove node 5. Then what we need to do is figure out how we get rid of node 5 and keep the rest of the tree properly connected. In this case, something simple we can do is move node 7 up and take the place of 5. And since 7 was just bigger than 5, it was just bigger than 5, it can actually fit here and be bigger than everything to the left and smaller than everything to the right. And, and so that particular substitution works well for removing 5. But in general, if we want to remove a node from the middle of the tree, we have to figure out how to organize the tree around it to compensate for it being removed. Theoretically, we can change the tree however we would like on a removal. For example, we could take every node out of the tree, take out the node we want, and then add everything back into the tree. But this would not be very efficient. What we'd like to do is make removal cost about the same thing as a search or an insertion, right? We don't want to do something that requires us to act on every node in the tree that's already there, because that would be at least order n if we were to do that, possibly much more. So that's our challenge with removal. And if you think about this, like you think about, if you go back and rethink about like removing a node from a linked list or maybe a doubly linked list, then we remember that removing things gets, pretty complicated. We have to figure out how to fix up all the surrounding pointers in order to ensure that the tree is still valid. And so that's what we're going to be trying to do. Figure out how we remove a node and ensure that the tree remains valid when we're done. Now, if we just think about this and we go look at a binary tree and we look at all the different nodes that we could want to remove, there are a few cases that we could just easily write out that we would need to solve. One of them is, what if we want to remove a node that has no children? It's a leaf node. Well, this turns out to be a very simple case. All we really have to do there is set the edge and its parent to null. Whether it's the left or right pointer, we have to figure that out, but then we just set it to null and we've removed the leaf. So that's the simplest case by far. Case 2 is when we have one child. And when we have one child, that means we're an internal node with a single child. And it turns out that this case is also pretty easy to handle, because when you have only a single child, you're kind of like a node in a linked list. And we are going to take advantage of that. The short answer is we set the edge and the parent of the node we're removing to point to the child. And that's good enough. That's going to work in general. And then the final case, like the one on the previous slide, is the case where there are two children. A node has two children, and we need to remove that node. This turns out to be a more challenging case, but we can actually say what we need to do in very simple terms. To make this work, all we really need to do is replace the node we're removing with its successor node. And because we know that its successor will honor all of the same relationships that it was honoring, it will be bigger than its left subtree, smaller or equal to its right subtree. And so this idea of replacing with a successor is intuitive and simple and will always work. Okay, here are an example of a couple of these cases, right? So case 1 was removing a leaf node. So let's say I want to remove 7. Well, all I have to do is set 5's right pointer to null, and then 7 is gone. So that's pretty simple. Likewise, if I wanted to remove 16, all I'd have to do is set 15's right pointer to null. Or if I wanted to remove 3, I could just set 5's left pointer to null, and they'd be gone. So case 1 is definitely the simplest case. Case 2, we have a node with one child. In this whole tree, there's only one such node, that's node 15. So if I want to remove 15, what I need to do is just connect 9 to its child directly. Now, why does that work? Because its child could be on either side. Well, it works because we know anything beneath 9 has to be bigger than 9. And so it doesn't matter if it's on the left or right side of 15. It has to be bigger than 9. And so it would be acceptable to take a child, whether it be 16 or whether it be over here 12, and just move it straight up here and connect it straight to 9. That's going to work. Right? So when we just remove 15 and directly connect 9 to its child node, then the tree becomes like this, which we can easily look at and verify is correct in this case. And we can also prove that in the general case. So these two are actually really simple things to reason through and not too hard to implement. The case 1 is kind of like removing the tail of a linked list. And case 2 is kind of like removing a node in the middle of a linked list. So we know how to do both of those things. Now removing a node with 2 children is the harder case. And so we're going to do this in 2 steps. We already know the basic idea. We find the successor node, and then we replace the node with its successor. We can imagine this being done in 2 steps. The first step is find and unlink the successor node, but don't delete it. Don't free it, because we're going to keep using that node. And then after we've done this, after we've removed the successor node, we replace the node that we want to remove with the successor node, and then fix up the left and right pointers as needed. As I've said before, this works because the successor node satisfies all the BST ordering constraints, right? It's larger than all the nodes in the left subtree of the node we're removing, and it's smaller than every node in the right subtree of the node we're removing. So it's the perfect candidate to stick in there to replace the node we're removing. Here's an example of case 3. So let's say I have this tree, and now I want to remove node 5. Okay, so what is the successor of 5? Well, the successor of 5 in this case is 7. And we need to use our algorithm to find this. And in this case, since 5 has a right subtree, 5's successor has to be in its right subtree. And in this case, 7 is the leftmost node in its right subtree. So that means 7 is the successor. And so all I need to do is unlink 7 from the tree. And then I'm going to stick 7 here. Right, and when I unlink 7 from the tree, it's going to set 5's right pointer to null. And that's important because what I'm going to do to stick it in the tree is I'm going to set 7's left pointer to point to 5's left pointer. I'm going to set 7's right pointer to point to 5's right pointer, in which case it'll be null now. And then I set 9, 5's parent, to point to 7. And then we're left with this tree as I've drawn it here. What if I wanted to remove 9 from this tree? 9 is the root. Well, if I want to remove 9, then I need to find the successor of 9, which in this case is the leftmost node in the right subtree. So that would be 10. That would be down here. So I'm going to unlink 10. And that means 15 will have a null pointer here. And then I'm going to put 10 up here where 9 is. So 10's left pointer will point to 5, 10's right pointer will point to 15, and then the root of the tree will now be 10. What about this weird case where I'm removing 9 again? This is a little bit of a weird case because when I come down here and I find the leftmost node in this subtree, I find 10, and you'll see that 10 has its own subtree. So when I remove this successor, I need to actually use the remove algorithm. It's not a leaf node, so I need to do something special here. So what do? Well, the nice thing we can observe is that when we remove this node 10, this node 10 can at most have 1 child, because if it had another child on the left, then that node would actually be the leftmost node and the smallest node. So we know that in the worst case, it has a child on its right, and we know therefore this boils down to case 2, not case 3, which is good. And so we can just connect 15 to 11 to remove 10. So removing the successor in this case, a little more complicated than previously, but still not too hard to do. We don't need to do a 2-child removal on the successor. If we did, we'd truly be in trouble, but we don't need to do that. And so 11 is going to move up here directly under 15, and then 10 is going to come up here and replace 9. So this is generally how the removal is going to work when we have two children. We find the successor, we remove the successor, and then we replace the node with the successor node. Okay, so the pseudocode for remove looks like this. And the overall part of this algorithm looks a lot like search and insertion. So we have a tree and a key that we're looking to remove. And we start out at the root of the tree. And then what we do is we're gonna search the tree until we find the node we want to remove. And this is just a normal search, right? We're looking for node key. If we don't find it, then we go to either the left or right, depending on the values. Now, because I might need to go up to the ancestors, I'm also tracking this parent node. There's a reason I need to track this parent node, because when I fix up the, when I fix up a node to point to, when I remove the successor, I'm sorry, when I remove the node and I substitute the successor in there, I need to set the pointer to point to the new node. And so the parent pointer to point to the new node. So this keeping track of the parents can allow me to set the left or right pointer within the parent to point to the new node properly. Okay, now when I find this node, then this is the case where I found the node I want to remove, but I haven't removed it yet. I haven't even started to remove it yet. I've just found it. So this whole piece of code here is just finding the node I want to remove. And then once I find it, I need to figure out, is it case 1, case 2, or case 3, and handle it properly. Okay, so if it's case 1, then the node has no children. And I can verify this by just checking, is node left equal to null and node right equal to null? And if they're both equal to null, I know it's a leaf node. Okay, if it turns out that that parent value I was tracking is also null, then that means I'm actually at the root of the tree. And so now the tree root's going to be null because I'm removing the root of the tree. Okay, if the root is not null and the parent's left node is equal to the node I'm removing, then I just set the parent's left node to null. Or if it's the right node that's the node I want to remove, then I set the right node to null. And that's all I need to do, right? I just need to have a pointer to the parent of the node I'm removing, figure out is it on the left or the right, and set that corresponding pointer to null, and then we're done with case 1. Okay, with case 2, this gets a little more involved, but a lot of it is just dealing with the fact that I might need to update the left pointer or the right pointer, and I have to figure that out. So again, I'm going to have an internal node with one child. And what I'm going to do is connect the parent directly to the child. Okay, so the first thing I have to figure out is which side of the node is the child on. So if node left does not equal null, that means the child's on the left. But if node right does not equal null, that means the child is on the right. So this first if statement is about figuring out the child is on the left, whereas down here, the child is on the right. And then the next thing we're going to do is connect the parent to that child based on the side that it's on. So if the parent is null, then that means, again, I'm removing the root. And so now I just set the root to be the child that I just previously discovered. In this case, in this top part, then the root is now the left child. Okay, else, if I'm not removing the root, then the parents, then if this node that I'm removing is on the left of the parent, then the parent's left pointer gets set to the child of the node, else the parent's right pointer gets set to the child of the node, which is on the left, right? Otherwise, we just do the reverse for the case where we're on the right of the parent and, I'm sorry, where the child is on the right, and now we might either be, again, on the left or right of the parent. So again, if the parent is null, that means we're replacing the root, and we set the root to be the child on the right. If the node we're removing is on the left of the parent, then we set the parent's left pointer to point to our child that's on the right. Else we set the parent's right pointer to point to our child that's on the right. Right, and then we're done. And that's case, and that handles the scenarios we need to handle for removing an internal node with one child. Okay, and then for the pseudocode for case 3, we need to handle the case where we have a node with 2 children. So the first thing we need to do in this case is find the successor node. And so what we're going to do is get a pointer to the right subtree. And what we do is we, once we're on the right subtree of node, we loop down its left side to find the leftmost node there. And once we find the leftmost node in its right subtree, we remove the successor node. And since removing that successor node could be case 1 or case 2, it will never be case 3, as we talked about before. It can't be case 3 because if it had a left child, we should go to that left child. At most, it can have a right child. So we can just reuse our case 1 and case 2 pseudocode to handle this case. And we just need to pass in the tree, the parent pointer, and then this node, the successor node that we're removing. In case 1 and case 2, we'll remove the successor node for us. And then we're left with a successor node that we can stick in the tree where our node currently is. So the successor node is available to be used. So we simply set the left of the successor to be the left of the node. We set the right of the successor to be the right of the node. And then we try to do the same logic we've been doing where we ask, are we removing the root node? And if we are, then the root becomes the successor. If we're not removing the root and the node is on the left of the parent, then the parent's left pointer becomes equal to the successor node, else the parent's right pointer becomes equal to the successor node. And then at that point, we're done with case 3. Okay, now we can come back and fill in this kind of high-level code for BST remove. So again, this while loop, it's just figuring out where the node is. Eventually, if the node we want to remove is a match in this statement, right? The data in the node is equal to the key we're trying to remove. Then we just have some code that looks like this. If we can apply case 1, then we're done. If we can't, then apply case 2. And if we can't apply case 2, then we have to be able to apply case 3. And then once we've done all these 3 cases, we free the node and we return. And we've finished. Okay, so the time complexity of binary search tree operations. Let's just go back over this again. So we've already talked about this once, but search has a big O of H, where H is the height of the tree. Insertion has a big O of H because it's basically just a search plus adding a node onto the bottom of the tree, right? Adding a leaf onto the tree. And then if we wanted to insert n nodes, then it would be n times H. And now if we want to remove a node, basically what we're doing is we search through the tree to find the node to remove. That's big O of H. And then if it's case 1 or case 2, we do a few operations and it's gone. If it's case 3, we have to do another search to find the successor, which could be big O of H, right? But that's just 2 searches in sequence. So we do one big O of H, then another big O of H. So that would just be 2H, which is still big O of H. Even in case 3, we maintain our big O of H complexity. And again, rewiring the tree to move the successor in and replace that node is just a few operations. It's constant time, and so that doesn't alter the big O complexity. Okay, so in the end of the day, removal is big O of H. So the nice thing here is we look down this list and we see search, insert, and remove, we're achieving O of H. And we know that H on a perfectly filled tree would be roughly log n, big O of log n. And so doing these operations on our binary search tree are pretty efficient. They're a lot more efficient than our linked list, which would order in. They're not quite as efficient as our hash table, which was constant time, but the advantage we get from our tree is that as we insert items, they're in order and they remain in order. And so we obtain a set that's both ordered and fairly efficient to search. Okay, so in summary, removal of a BST node involves three key cases. One, removing a leaf node. B, removing an internal node with one child. Or C, removing a node with two children. The first two cases are relatively straightforward and do not require significant rearranging of nodes. Removing a node with two children requires first removing the node's successor and then replacing the node with its successor. And we walked through some pseudocode for how that could be done.